Hello, your paper for this semester is semiconductor physics, and you got three modules, and I'll be teaching one module. And this is the first module with which we will begin. It's all about semiconducting diodes, their properties, applications, and um, behavior of semiconductor diodes under different types of biasing. So most of the content, I guess, is familiar to you, but there are some topics which are new and interesting. For example, thermistors. You may not have heard about thermistors before. That's all what this first module is about. And the reference that you can use is listed out here. These two textbooks are almost the same. You can use any of them. And BL Tereja, Basic Electronics, and Applied Electronics by R.S. Setha. If you prefer to use the second one, it is the latest edition. If you buy, you will see that it is highly illustrative and useful, and there are many copies available in your library. You can take copies and refer. So anyway, this is where we will begin semiconductor diodes and their applications. So before we begin, as I told you earlier, this is a topic which you are familiar with. So there are some content from your +2 classes or from your school textbooks that you'll have to syllabus that you'll have to revise. That is metals, insulators, and semiconductors. You have to please go through the difference between metals, insulators, and semiconductors in terms of their conductivity and band gap. Then you might have also learned what is intrinsic and extrinsic semiconductors. Please go through them. Then another thing that you will need before we begin the first module is an idea about crystalline structure of semiconductors. What is crystal and what is amorphous, some examples for crystalline materials. Then you must also it will be useful if you have a basic idea about the atomic arrangements inside silicon and germanium, because these two are the most important semiconducting materials that we use in electronics. Then you must also go through the topic p-type and n-type semiconductors. And it is also nice if you could find out how much is the band gap of silicon and germanium. It's very easy nowadays because you just have to type in Google and it will tell you how much it is. But what is the unit in which it is given? Say, for example, when we say band gap, it is energy band gap, so we expect that to be in joule, but you will see that most of the websites will be giving you the answer in electron volt. So it is also nice if you know how you can convert between electron volt and joule. So that is what you have to find out before we proceed to the first module. So in session 1, I have listed out only two objectives. They are PN junction and depletion region. We will see what is a PN junction and how a depletion region is formed, and when a depletion region is formed, how is it going to affect the flow of charge carriers across the junction. And to get an idea about those features, let us begin with the example of silicon. Why silicon? It's one of the most important semiconducting material which is used for making most of the electronic components that you handle in the electronics lab, like diodes, transistors. So it's nice to know what is the atomic arrangement of silicon. Silicon is an example of a crystal. So you know that crystal is a material which will be having regular arrangement of atoms. regular or periodic arrangement of atoms. You can see the silicon atoms, which is shown using this blue circle. It is repeating at regular intervals in space, and you got a layer of silicon, and on top of that you will be having a similar layer, and on bottom also you will be having a similar layer. And that's exactly what we mean when we say regular arrangement of atoms. A crystal will be characterized by the regular arrangement of atoms, and the locations where you can see the atoms, if you just put some points at those locations where you expect to see the atoms, you'll be getting a set of points which are periodic, and that set of points is what we call the lattice. Lattice is an array of points, and when you put atoms at those lattice points, you'll be getting the crystals. And the atoms, or the group of atoms that you put at each of the lattice locations, they are referred to as bases. So the lattice points occupied by the basis atoms or basis group of atoms will constitute the crystal. Now silicon is an element from the fourth group, which means, see, this is the atomic arrangement. Its atomic number is 14. The atomic arrangement, you can see the outermost shell will be having 4 electrons, or the valency is 4. But in order to complete the octet, it needs 8 electron, but it has only 4 electron. So how it is going to complete the valency? It needs 4 more electrons. So if you examine the diagram on the right, you can see the middle silicon is borrowing, not borrowing, they are sharing. The middle silicon is sharing its outer electrons with 4 neighboring silicon atoms. So you can see the silicon at the center, it has 4 electron on its own, and by sharing 4 electron or 1 electron each from 4 adjacent atoms, it will complete its valency and it will become stable. So when the silicon is in the crystal lattice, it will be making these bonds with the adjacent silicon atoms, and these bonds will be having 2 electrons each, or one bond between 2 silicon atoms will be carrying 2 electrons, and those 2 electrons are the valence electrons. Now valence electrons are a part of the bond, and the valence electrons is what make the crystal stable. So when an electron is in the valence band, or when an electron is in the bond, that electron is not free to move. So that is referred to as valence electrons. So all these electrons which are shared between these atoms, they are making covalent bonds, and they are referred to as valence electrons. And when they are valence electrons, they will be present in the valence band in terms of energy. But somehow if you can give energy, you can make this electron free. You can break the bond, and when you break the bond, the electrons will become free, and that electron will get more energy, and it will go to a higher energy state, which we call the conduction band. So the electrons which are present in the conduction band are free to move, and they are capable of making current, whereas the electrons which are present in the covalent bonds will be present in the valence band, and they are not free, and they are part of the bond of the material. Now that is about this pure semiconductor, and pure semiconductors are not as such used in electronics. You will have to make them impure by doping it with proper impurity atoms, so that it will be having an enhanced conductivity. So in that process, you have probably heard about p-type material and n-type material, and those materials are referred to as extrinsic semiconductors. Pure semiconductors doped with some impurity atoms are referred to as extrinsic semiconductors. So in order to make p-type material or n-type material, you have to make use of atoms as dopant from very different groups. For example, if you want to make an n-type semiconductor, that will be having excess electrons. So the impurity atoms that you're using should have extra electron than what is required to complete the octet. So that means, for example, if you are choosing an atom from fifth group, and if you are doping it in the silicon atom, for example, in the previous diagram, if the silicon at the center is replaced by this material, which is Sb, antimony. Antimony has got 5 electrons, whereas that will be surrounded by 4 silicon atoms, and that those 4 silicon atoms can share 1 electron each with this antimony. So that will make 9, 5 from the valence band or outer shell of this antimony, and 4 each contributed by the neighbors, and that will make 9, which is not required. 8 is sufficient, so that 1 extra electron will be free, and it becomes it is not capable of being part of any bond, and it will be free, and it will go to the conduction band. So that will make so depending on, for example, if you have got 1 antimony impurity atom, that will contribute 1 extra electron, free electron. 2 antimony atoms will contribute 2 electrons. So like that, depending on the doping concentration, you will be having some free electron concentration, and that will make that material n-type. N-type means it will be having excess electrons, and those electrons will make conductivity possible in that material. And one thing that you have to remember, similarly, if you are using an element from the third group, which is having only 3 electrons in the outer shell, when it is shared by when this, for example, boron, it is referred to as an acceptor impurity atom, and if boron is replacing one of the silicon in the previous example, for example, the middle silicon, suppose it is replaced by boron, then that middle boron atom is having only 3 electrons, and the 4 neighbor silicon atoms will contribute 4, and it will making 7, whereas it required 8, which means it is deficient in 1 electron, and that deficiency location is referred to as a hole. So depending on the number of this type of impurity is referred to as acceptor impurity. So depending on the number of acceptor impurity atoms, or the concentration of the acceptor impurity atoms, the material will be having excess holes, and these holes are also capable of creating current. Now another thing that you have to keep in mind is we call this to be the p-type material and n-type material. Only thing is that it will be having excess holes and excess electrons, but you will have to always remember that even after doping, the material will remain electrically neutral, because this extra electron was actually part of the dopant atom, and the dopant atom, it's not losing any electron. Only thing is that when it is replacing another silicon atom, that 1 electron is becoming extra, or 1 electron is becoming deficient, and it doesn't make ionization in that material, or this is not making that material electrically charged. The material will remain electrically neutral. Now the formation of p and n type material. See, if you are replacing, so this is a silicon substance, and you have adopted boron. Boron is from the third group. It is having 3 electrons in the outer shell. So if a middle silicon is replaced by boron, then as I explained earlier, it is making 7 electron, and it is deficient in 1 electron, so that deficiency is a hole, and this material becomes p-type. P-type means it will contain excess holes but electrically neutral. It will contain excess holes, but the material will be electrically neutral. And another thing is, these holes in the p-type material is referred to as majority carriers. Now on the other hand, you have got the n-type material, which is doped with donor type impurity, which is capable of donating extra electrons. That's from the 5th group. Example is antimony. So it is when it is doped, one electron is extra. It is not required by these bonds, so it becomes extra, but it is part of this antimony, and that extra electron will make this material n-type, and here the majority carriers are n-type. Now another thing is that both these materials, p-type and n-type, they will all also contain minority carriers due to some defects in the system. So the minority carriers in p-type are electrons, and the minority carriers in n-type material are holes. Now when you form a PN junction, what will happen? You have got a p-type material on one side and n-type material on the other side, and you are joining them together. It's not just you manually join them together. It's actually a a thin film deposition stage. You have got a wafer or a substrate on which you have got a film of p-type semiconductor, and over that you got a thin film of n-type semiconductor, and in between you have got the junction. So when you form the junction suitably, what we are going to see is, for example, you look at the top diagram. You have got the n-type material on the right side. All these black dots are extra electrons. They are the majority carriers, and at the on the middle, the diagram below, you can see when you form the junction, what's going to happen is that on the right side you have got a large number of electrons, and on the left side inside the p material you have got some number of electrons which are minority carriers. So there will be a flow of electrons from right to left, because high concentration of electrons on the right side and low concentration of electrons on the left side. So due to the concentration gradient or difference in concentration, the charge carriers will move from high concentration region to low concentration region. So that means electrons will move from right to left, and similarly holes will move from left to right. So essentially both these charge carriers, holes and electrons, they will cross the junction and reach the other side. And just imagine one electron which is moving from the right to the left. When they reach the left side, there are already many holes. So when the free electrons are coming, they will meet the hole and they will recombine and they will disappear. So that is what is happening when we form a PN junction. So initially there is a movement of charge carriers, and you know that whenever the charge carriers are moving, whatever be the reason, that will be called a current. And in this case the current or the movement of charge carriers is due to the concentration gradient. So we call this current to be the diffusion current. The process of movement of these charge carriers is diffusion. Diffusion is the movement due to the concentration difference, and the current constituted by that movement is called the diffusion current. And the sign, or for example, just like in the case of a metal, when you are connecting it to a battery, you can make the electrons move and it will make a current. Similarly here, we haven't used any battery, we have just formed the PN junction, and the charge carriers are moving because of the concentration gradient, that it makes a current which we call the diffusion current. And the holes are moving from left to right and the electrons are moving from right to left. And unlike in the case of metals, here we have got two different type of charge carriers, holes and electrons. They are moving in the opposite direction, but both will constitute current in the same direction because they are having opposite charge. So even though their movements are in the opposite direction, they will make current in the same direction because they are having opposite charges. So when you measure the current, the total current will be the sum of the current by the hole and the current by the electrons. So that is what is happening in the beginning when we form the PN junction. Now at the middle I have drawn a diagram in which on the right side near the junction in the N region you can see some positive sign which is encircled. You have got some special meaning is attached to that symbol. That means, when one electron is moving from the right to the left, that electron is the free electron that was part of the dopant atom. Now that electron is moving and it is reaching the p side. So that means when one electron is moving that way, one dopant atom has lost one electron, and that atom has become ionized, and that is what is shown using this plus sign within a circle. So normally when you draw, for example, p-type material, you can, here in this diagram holes are shown, but you can also show the p-type material as positive sign. But when you use that, the positive sign over the p region will not be within a circle, but the positive sign in the n region will be within a circle, and those two are having two different meanings. When you have got a charge or this plus and minus symbol which is written inside a circle, it means that is a charge which is due to the presence of ion. Whereas if you have got a positive charge on the p side, it is not encircled, which means it is a free hole which is capable of moving, whereas this encircled plus sign is not capable of moving. It is a static charge because it is an ion which is fixed in the lattice, because it is the dopant atom which is replacing one of our semiconductor atom, like for example silicon. And when it is replacing silicon, that dopant atom is fixed in the lattice, and if it is losing an electron, that ion is also fixed in the lattice and it cannot move. So all the charges which are encircled are stationary charges, whereas other charges which are not encircled are free charges or charge carriers. So this is what is happening when we form the junction. You charge carriers move across the junction, recombine, and the atoms which are losing that charge will become ionized, and it will become positive ions on the n side and negative ions on the p side. So just near the junction, you have got a layer of fixed charges. So this region now they do not have any more moving charges. It has charges, but those charges are ions and they are not capable of moving. So this region, which is shown within this curly arrow, it contains charges which are not capable of moving, or we say that region is depleted of moving charges, and therefore that region is referred to as depletion region. Now to sum up, we have learned that doping with suitable impurities can lead to the formation of extrinsic semiconductors, and while in contact, p and n type materials will form PN junction, and at the junction there is a depletion region, and that depletion region is devoid of moving charges. Now coming up in second session, we will continue with this, and we are going to learn potential barrier developed across the PN junction, and mathematical equation for diffusion current. Then we will see the changes in the barrier when we give forward and reverse bias, and barrier height formation and depletion layer width modification when we give a bias. So that's what we are going to learn in session 2. Okay, so long. So if you have got questions, you can post it in the group, and I will try to answer.